Hi guys, I will explain the moment of area part 6, principle and the proof of a Mohr circle. From Mohr circle and the second and the product moment of area to summary. Here I have a quiz for you. Which of the following best describes the direction of the green and the blue axis in the coordinate system with respect to the Mohr circle here? I explain the topics from the first moment of area to the direction of principal axis and the section shape. In this video, I will explain the principle and how to prove the Mohr circle. Remaining topics will be explained in the next videos. As I explained in the previous videos, the second and the product moment of area Iz prime, Iy prime, Iz'y prime about the new axis rotated by theta from the reference axis can be expressed by the three equations on the left. All appears as functions of second and product moment of area Iz'y, Iy, and Iz'y about the original axis. By changing the square term of these three equations into 2 theta using the trigonometric identities, it can be expressed as three expressions on the right with the 2 theta terms. Substituting the angle increased at regular intervals, such as every 1 or every 2 degrees, from 0 to 180 degrees, into theta of the three equations Iz prime, Iy prime, and Iz'y prime, and displaying that result in a coordinate system with the second moment of area as horizontal axis and the product moment of area as the vertical axis, it appears as a circle as shown in the figure on the right, which is called Mohr circle. How can the Iz prime, Iy prime, and Iz'y prime be expressed in terms of Iz'y, Iy, and Iz'y through the Mohr circle? I will explain and prove this principle by geometric analysis. Before proceeding with the principle and the proof of the Mohr circle, let's first look at how to draw the Mohr circle. As a step 1, draw the axis of Mohr circle. In the Mohr circle, the second moment of area appears on the horizontal axis, and the product moment of area appears on the vertical axis. The positive horizontal axis direction must be in the same direction as the positive horizontal axis direction z of the section. As a step 2, the origin C of the Mohr circle is calculated. The origin of the Mohr circle is the average value of the second moment of area about each axis. In the step 3, to calculate the radius of a Mohr circle, we compute the quantity of I which is the half of difference of second moment of area about each axis. In the step 4, just draw the size of product moment of area Iz'y as a horizontal line. In the step 5, since we know the product moment of area Iz'y, which is the height of right triangle ZAC, and I deep, which is the base of right triangle ZAC, we can calculate the radius r, which is the hypotenuse of right triangle. Therefore, from the right triangle ZAC, the radius r of the Mohr circle can be calculated in this equation. In the step 6, draw the Mohr circle using the radius r obtained in the previous slide and describe the second moment of area Iz'y about the z-axis, and the second moment of area Iy about the y-axis, and the second moment of area about the major axis I maximum, and the second moment of area about the minor axis I minimum. As the seventh step, calculate the angle to the principal axis. We calculate the first angle from the current horizontal axis to the principal axis on the Mohr circle using the equation for calculating the position of the principal axis described in the previous video, E0045. Note that the rotation of coordinate axis in the rear section is doubled in the Mohr circle. And also remember that the second angle to the principal axis is 2 theta p plus pi. I explained that in the previous video, E0044. Equations and the Mohr circle, their values do not change even when the axis rotates on the cross-section, which is called invariant. The radius r of the Mohr circle, the second moment of area I max about the major axis, and the second moment of area I mean about the minor axis, the average value I average are all invariants. The length ZABY is also invariant if it rotates integrally with the radius r with the same shape as it is. Using these invariants that do not change, the second and the product moment of area about the rotated coordinate system can be obtained geometrically. If the coordinate axis rotates by theta in the actual cross-section, the radius of Mohr circle rotates by 2 theta, which is twice in the Mohr circle. Since ZABY of the existing coordinate system has exactly the same shape and length as Z prime, A prime, B prime, Y prime of the coordinate system after rotation, it can be used to calculate the second and product moment of area about the new coordinate system, Z prime, Y prime axis. What we know are Iz'y, Iy, and Iz'y in the ZY coordinate system, and what we need to know are Iz prime, Iy prime, Iz'y prime in the ZY prime coordinate system. In the figure, green indicates second and product moment of area about the ZY axis before rotation, and the blue indicates the second and product moment of area about the ZY prime axis after rotation. Since R and I maximum and I minimum and I average are all invariant, they are the same regardless of axis rotation. Let's understand this with an example of a real cross-section. The rectangular cross-section on the lower left figure shows the real example of a Mohr circle on the right figure. As the positive z-axis rotates counterclockwise and moves to the z-prime axis, the product moment of area decreases and the second moment of area increases. It can be seen that the direction of rotation in the Mohr circle and the direction of axis rotation in the actual section are the same, according to the 2 theta term in the related equations. The rotation angle theta in the actual section is doubled in the Mohr circle as 2 theta. Remember that the green dotted line before rotation and the blue dotted line after rotation are exactly the same shape and size. Using the geometric properties of the Mohr circle, let's derive the equation for the second moment of area, Z prime, of the rotated coordinate axis. Z prime we want to find is the value obtained by adding the horizontal component of Z prime C to the I average. And the horizontal component of Z prime C is the sum of two components. The horizontal component of Z prime A prime and the horizontal component of A prime C. In the figure, the horizontal component of A prime C can be calculated as in the equation 1. And the horizontal component of Z prime A prime can be calculated as in the equation 2. Here, theta has a negative value because it is counterclockwise. So the entire term of the equation 2 has a positive value. Referring to the figure, adding equation 1 and 2 gives the horizontal component of Z prime C, and adding I average to that results gives Iz prime. Consequently, we can get the final equation to calculate Iz prime. Let's look into that geometric analysis in detail. Let's first calculate the length A prime P, which is the horizontal length of A prime C. Since the green dotted line and the blue dotted line are exactly the same, the line segment AC equals A prime C, which can be expressed as the equation 5. Since the rotation angle of the coordinate axis is 2 theta in the Mohr circle, the length A prime P can be expressed as the equation 6. Now let's calculate the length of QA prime, which is the horizontal component of Z prime A prime. Since the green dotted line and the blue dotted line are exactly the same, the line segment ZA equals Z prime A prime, which is the same as the product moment of area Iz'y. So it can be expressed as the equation 7. Since the rotation angle of the coordinate axis is 2 theta in the Mohr circle, the length QA prime can be expressed as the equation 8. As shown in the figure, the second moment of area about the Z prime axis must be greater than that about a Z axis. Since 2 theta has a negative value in the counterclockwise direction, a sign minus is added to make the length of the line segment QA prime a positive value. Therefore, if we add the horizontal component of A prime C of equation 1, horizontal component of Z prime A prime of equation 2, and the average value I average of equation 4 altogether, we can get the Iz prime as expressed in the equation 3. This geometrically proves that we can find the Iz prime we need to know using the known values Iz'y, Iy, and Iz'y. This time, using the geometric properties of the Mohr circle, let's derive the equation for the second moment of area Iy prime of the rotated coordinate axis. The Iy prime we want to find equals I average minus the horizontal component of Cy prime, which is the sum of two horizontal components, the horizontal component of Cb prime and the horizontal component of B prime Y prime. The horizontal component of Cb prime can be calculated as in the equation 9. And the horizontal component of Y prime B prime can be calculated as in the equation 10. Here, theta has a negative value because it is counterclockwise, so the entire term of equation 10 has the positive value. Adding equations 9 and 10 gives the horizontal component of y prime c, and by subtracting that value from the I average, we can get Iy prime. Consequently, we end up with the final equation to calculate the Iy prime. Let's look into that geometric analysis in detail. Let's first calculate the length Cp, which is the horizontal length of Cp prime. Since the green dotted line and the blue dotted line are the same, the length segment Cb equals Cb prime, which can be expressed as the equation 13. Since the rotation angle of coordinate axis is 2 theta, the length of Cp can be expressed as the equation 14. Now let's calculate the length of Qy prime, which is the horizontal component of B prime Y prime. Since the green dotted line and the blue dotted line are exactly the same, the line segment By equals B prime Y prime, which is the same as the product moment of area Iz'y. So it can be expressed as the equation 15. Since the rotation angle of coordinate axis is 2 theta, the length of Qy prime can be expressed as the equation 16. Since 2 theta has a negative value in the counterclockwise direction, a minus sign is added to make the length of the line segment Qy prime a positive value. Therefore, horizontal component of Cy prime can be obtained by adding two components. The horizontal component of Cb prime over equation 9 and the horizontal component of B prime Y prime over equation 10. Subtracting those values from the I average equation 12 gives Iy prime as shown in the equation 11. This geometrically proves that we can find the Iy prime we need to know in terms of the noun values Iz'y, Iy, and Iz'y. Let's go ahead and derive the expression for the product moment of area Iz'y prime of the rotated coordinate axis Zy prime using the geometric properties of Mohr's circle. In the figure, the vertical component of A prime C can be calculated as the equation 17, and the vertical component of Z prime A prime can be calculated as the equation 18. Here, theta has a negative value because it is counterclockwise. So, the equation 18 have a positive value. Subtracting the equation 17 from the equation 18, the product moment of area Iz'y prime can be obtained. Let's take a closer look at this. First, let's calculate the length Z prime P, which is the vertical length of Z prime A prime. Since the green dotted line and the blue dotted line are exactly the same, the line segment ZA is the same as Z prime A prime and can be expressed as the equation 21. Since the rotation angle of coordinate axis is 2 theta, the length of Z prime P can be expressed as the equation 22. Now let's calculate the length of QA prime, which is the horizontal component of A prime C. Since the green dotted line and the blue dotted line are exactly the same. The line segment AC equals A prime C, which can be expressed as the equation 23. Since the rotation angle of coordinate axis is 2 theta, the length of QA prime can be expressed as the equation 24. Therefore, subtracting the vertical component of A prime C of the equation 17 from the vertical component of Z prime A prime of the equation 18, we can get the expression Iz'y prime directly. This geometrically proves that we can obtain the Iz'y prime we need to know from the known values of Iz'y, Iy, and Iz'y. What a complicated figure we have! Although complicated, the figure on the right shows how the unknown second moment of area can be expressed with the known second moment of area Iz'y, Iy, and the product moment of area Iz'y when the rotation angle theta is counterclockwise. Green represents the term of sin theta, and blue represents the term of cosine theta. Using those relationships, we can obtain the second moment of area for a new coordinate system with arbitrary angle theta. We have another complicated figure. This figure on the right shows how the unknown product moment of area can be expressed with the known second moment of area Iz'y, Iy, and the product moment of area Iz'y when the rotation angle theta of coordinate axis is counterclockwise. Green represents the term of sin theta, and blue represents the term of cosine theta. Using those relationships, we can obtain the product moment of area for the new coordinate system with arbitrary rotation angle theta. The answer to the quiz is number 2. In number 1 and number 3, the original axis marked in green is the principal axis, as you can see here, but the green axis indicating the original axis in Mohr circle is not the principal axis. Number 2 is the answer in line with the diagram of Mohr circle because the second moment of area gets bigger and the product moment of area becomes smaller as it rotates from the original green axis to the rotated black axis. Here we have a summary. The second and the product moments of area can be expressed using the Mohr circle. It can be proved that the second and the product moments of area can be represented by Mohr circle using the geometry analysis. The direction of rotation angle of the coordinate axis on the cross-section is the same as that of Mohr circle. The angle of rotation in the Mohr circle is twice that of the coordinate axis in the cross-section. Using the Mohr circle, we can easily find the second and product moments of area for a coordinate system with an arbitrary rotation angle. If the reference coordinate axis and the axis of Mohr circle are in the same direction, both the rotation angle of the coordinate axis and the Mohr circle are also in the same direction. If you watch the previous videos, you can easily understand the upcoming videos. In the previous video, E0045, I explained the way to calculate the location of principal axis using the fact that the product moment of area equals 0 in the principal axis. Recently, I explained the relationship between the location of principal axis and the sign of product moment of area through practical example. The next video will be Price Tier Part 18, Moment of Area Part 7. I will explain the way to draw the Mohr circle and to calculate the new second and product moment of area for a coordinate system with an arbitrary rotation angle theta using Mohr circle. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you in next video. Goodbye guys!